All right, let's look at what's called this reaction energy profile. This is looking at the idea of a graph to illustrate not only where a reaction is occurring, how much energy it takes, but kind of what are the different parts of that profile. Often you'll be needing to interpret one and occasionally draw one or modify one over time. So reactions often when we think of these is breaking bonds and forming new bonds. The idea is that they have always needing energy to be put in to break those bonds, and we are releasing energy when bonds are forming. The idea is that there is a sum of this entire part, and that's called the enthalpy of reaction. We can see that this one is overall negative, meaning exothermic and more stable than what it started off as. So here's it kind of broken down that the reaction coordinate is the progress of the reaction. So you see reaction progress from beginning reactants to the end product. Now looking at this example, all of the necessary bonds are broken at the top of the peak. This is what's called the activated complex. Now, the activation energy needing to be supplied is to break off these bonds right here. However, new bonds form, and this forms right at the trough here, which is what we think of as the products. Now you can see this reaction happens in two steps. So right here, this trough is what we have as our product. This needs additional energy because what's occurring is breaking more bonds to get to the activated complex kind of number 2. And then finally at the end, we get what we consider to be our product, this CH3CH2Cl. So the activation energy goes from the reactants to the highest peak, that even though this activation energy here is also present, this is the predominant one needed because of its height. The change in reaction, that negative 113, would be the difference between the reactants and the products. So there's a lot of energy going on to get the reaction going, continued, to get to the end point of where we're at. Now, the effective temperature on rate we've talked about in a, what do you want to call it, qualitative sense without looking at it quantitatively. Changing the temperature changes the rate constant, K, of rate law. We haven't talked about really how or why, but this is meant to kind of illustrate a representation found by Arrhenius back in the day. Now, temperature is in kelvins, gas constant provided. The frequency factor is just the rate the reactant energy approaches activation energy. We can consider that just to be a constant value. Don't look too much into it. And then activation energy, what we've been talking about so far. So we see that there's this exponential factor. This exponential factor here is between a 0 and 1. Okay? This represents the fraction of reactant molecules with sufficient energy that make it over the barrier. So what we're trying to talk about here is that the rate constant is going to change based upon these factors. The higher the activation energy, the fewer the molecules have enough energy to overcome it. That extra energy comes from converting kinetic energy of motion to potential energy in the molecule when the molecules collide. So a couple of things. Increasing the temperature increases the average kinetic energy of the molecules. Therefore, increasing the temperature will increase the number of molecules with sufficient energy. Therefore, increasing temperature will increase reaction rate. So I threw in some numbers. Again, these are just meant to be an idea. If we had a baseline, activation energy of 20, temperature of 300 Kelvin, R doesn't change, A doesn't change. We get a K of, I just said this was like 1, of 0.992 when you take that e to the negative A. If we cut the activation energy in half, you see that this factor goes up. If we decrease the temperature, you see it goes down. If you do it both, decrease the activation energy and increase the temperature, it goes up to its highest point yet. So the concepts that we talk about here is the fact that a decrease in activation energy and increase in temperature will increase the reaction rate because of this equation. So the idea is that this is quantitatively showing this increase as opposed to just talking about it. And we'll get back to 5-4 in a moment. All right, come in with any kind of questions. We'll talk about it. Remember, we're not doing calculations with this, but you might need to be able to use this to explain why we have these increase in reaction rates concerning activation energy and temperature. Take care.